Eighth lecture. In this lecture, we'll continue studying some basics about operational amplifiers. We started studying operational amplifiers a couple of lectures before. Uh, in this lecture, we will study bias current compensation. Bias current is the current that we get at from the output to the input terminal or in the flowing into the input terminal when we don't expect it. For example, for an inverting amplifier, this point is virtual ground and there should be no current flowing if we apply a Vn is equal to 0 volt. But due to mismatch of transistors, there is a small output voltage, the error output voltage, which causes a current to flow through RF, and we have this resulting V out at the output. So this V out is due to this bias current I1, which is not desired. It's an undesired current, right? In case of a voltage follower, we have this undesired current I1 flowing the into the inverting terminal, into the non-inverting terminal when we haven't applied a voltage, a non-zero voltage. In fact, we have applied a 0 volts here, but still we have an input current due to leakage of transistor, and due to this we have this I1 times RS voltage here with respect to ground, because the left hand side of this resistor is ground. So if we have I1 RS voltage here, so the voltage drop across RS or from this input terminal to ground is I1 RS. And since it's a voltage follower, the same voltage would be appeared at the output with the negative sign because the input is grounded, the left hand side is at a smaller voltage. So even in a voltage follower circuit, we have this leakage current, and due to this current, we get an erroneous output, an error output. And in the non-inverting amplifier, if we apply a 0 volts here, we should get a 0 volts here, but we don't get that. We get a non-zero voltage equal to I1 times RF. So in all three circuit topologies, we apply a 0 volts at the input, but we don't get a 0 at the output. So that's embarrassing. We shouldn't get this 0. We should get 0 volt at the output when we apply a 0 volt at the input. But due to mismatch of transistors and due to leakage currents, we get non-zero output, the error output voltage. So it's undesired. In all three cases, this voltage, the erroneous output voltage is undesired. In the next slide, we are going to study how would we compensate this error voltage V out error. So now we'll study three techniques for three different circuits to get rid of this error voltage or to compensate for that. Right. How do we do that? For an inverting amplifier, we see that the input impedance or the input resistance that we see from the negative terminal is Ri in parallel with Rf. So we put an equivalent resistance Rc, that is Ri in parallel with Rf in the non-inverting terminal. That compensates or equalizes the two resistances, and the output voltage is 0 volts when the input voltage is 0. For a voltage follower circuit, we have to have a feedback resistor Rf that is equal to Rs. This voltage, this resistor, that is the source resistor, the internal source resistance of this Vin source. And for a non-inverting amplifier, we can have the same arrangement, Ri in parallel with Rf, connected as one resistor in the non-inverting terminal. So that compensates the effect. And now we have equal Is flowing through the two terminals. This means the input offset voltage is 0 and output is 0. So that somehow compensates for input bias currents. Right. In order to make the output voltage is equal to 0 when the inputs are not 0. Due to mismatch of transistors, if we apply 0 volts on both inputs, the output is not 0. This is due to mismatch of transistors. So the remedy for this is applying an input offset voltage. Input offset voltage is applied by the user. We apply it externally, a voltage source, and we call it VIO. And we adjust this VIO, the input offset voltage, to make the output voltage equal to 0. So we adjust this VIO input offset. So VIO is the required DC voltage at this for this voltage follower circuit, for example. We require this voltage VIO at non-inverting input. We adjust it and make the output Vout is equal to 0. Right. For a remedy in a commercially available op-amp 741, a 741 is available as an 8-pin dual inline package where we have 4 pins on left side and 4 pins on right side. Pin number 1 is offset null and pin number 5. 1 and 5 are offset null. 2 is inverting input, 3 is non-inverting input. 4 and 7 are the negative and positive supply voltages. 6 is the output and 8 is not connected, and C means not connected. So between 1 and 5 we are given 2 pins for offset null. So what we do is we connect a resistor of value 10k, and that's a variable resistor between 1 and 5. And the third terminal of the variable resistor is connected to 4, that is minus V. 7 is plus V, the supply voltage. Right. So the third terminal is connected to minus V, and the other 2 terminals are connected between 1 and 5, and then we vary it. It's a variable resistor. We vary it unless we make V out is equal to 0 volts. So as long as we keep on moving this unless the output voltage V out is 0 volts. So this is the remedy for output. The remedy or the input offset voltage applied for 741 op-amp to bring output is equal to 0 when the 2 inputs are grounded. So we can connect the 2 inputs to ground is 2 and 3. The inverting and non-inverting inputs are connected to ground, and the output is brought to 0 by adjusting this 10k resistor by taking care of, actually this takes care of the mismatch in the transistors that are implemented within this 741 op-amp. So that's great. If we use this 10k resistor, we can apply an input offset voltage to bring V out is equal to 0 volts when both inputs are 0. Right, we will keep on studying more about operational amplifiers in our upcoming lectures. Thank you.